Everything we thought we knew about Jupiter is wrong. Not slightly wrong. Not correctable. Wrong in a way that breaks the entire foundation of how we think planets are born. And the most unsettling part, we've known for years, and we still don't have an answer. In 2017, NASA's Juno spacecraft did something no probe had done before. It got close, dangerously, intimately close to Jupiter, and it started measuring. But here's the problem. The data that came back didn't match our models. Not partially, not almost. The measurements contradicted every major theory about what lives inside Jupiter's core. Scientists sent the data to independent teams worldwide. The answer came back the same. Something was fundamentally, catastrophically wrong. For over 4 centuries, humans have been staring at Jupiter. Galileo tracked its moons in 1610. We sent Pioneer, Voyager, Ulysses, Cassini, Galileo, the spacecraft, all past it. We were so certain we understood it, we weren't even close. What Juno found at Jupiter's center, the core that was supposed to anchor everything, wasn't solid, wasn't absent. It was something no model had ever predicted, something that doesn't fit neatly into any category we have. They gave it one word, fuzzy, and that single word unraveled decades of planetary science. Before Juno, there were 2 dominant theories about how Jupiter formed, 2 camps. Decades of debate, careers built on both sides. Theory 1, core accretion. A solid ball of rock and ice accumulates at the center over millions of years. Once it's massive enough, gravity pulls in hydrogen and helium from the surrounding nebula. The core comes first. The gas cloud follows. Clean, logical, layered. Apparently wrong. Theory 2, disk instability, no solid core needed. A region of the solar nebula becomes gravitationally unstable and collapses in on itself almost instantly. 1,000 years in astronomical time. Pure gas all the way down. Also apparently wrong. Juno's measurements broke both theories at once. Not one. Both. Simultaneously, the heavy elements, the rocks, the metals, the ices that should form a key or central core, aren't sitting neatly at the center. They're dissolved, smeared outward to nearly half of Jupiter's total radius, blending into the hydrogen above with no defined boundary, no sharp edge, no clear transition, and that is where everything breaks. Our entire standard model of giant planet formation requires a solid, discrete core to trigger the process. No solid core means the process shouldn't start. But Jupiter, the largest planet in our solar system, clearly exists. This shouldn't exist, and yet it does. The spacecraft that saw through a giant you cannot drill into Jupiter. At its core, the pressure would compress any material we've ever built into something unrecognizable. No probe could survive the descent. So how did Juno see inside it? Gravity whispers. Every planet's gravitational field carries hidden fingerprints, microscopic variations depending on what's buried within. Dense material pulls harder, lighter material pulls softer. From the outside, those differences are almost invisible. Almost. Juno was engineered to hear those whispers. It dove to within 4,200 kilometers of Jupiter's cloud tops, closer to Jupiter's surface than the International Space Station orbits above Earth, and broadcast a continuous radio signal home. Here's where the engineering becomes almost unbelievable. Scientists measured changes in Juno's speed caused by gravitational variations in Jupiter's interior. The precision required? Detecting shifts of fractions of a millimeter per second from 600 million kilometers away. That's like hearing a whisper from the other side of the solar system. Pass after pass, angle after angle, year after year, Juno built the most detailed gravitational map of Jupiter ever constructed. And the map told a story nobody wanted to hear. Jupiter's interior wasn't behaving like a planet with a solid core. It gets worse. It also wasn't behaving like a planet without one. It was behaving like something with no name in our textbooks, what fuzzy actually means, and why it's terrifying. Imagine a hard-boiled egg. Solid yolk at the center, clear boundary between yolk and white, defined layers. That's what a planet's core was supposed to look like. Now imagine someone shook that egg for a billion years. The yolk dissolves. It bleeds into the white. The boundary disappears. You can no longer say where yolk ends and white begins. The whole thing becomes diffuse. That's Jupiter's core. Heavy elements dissolved and spread across a region spanning nearly half the planet's radius. No clear edge. No defined boundary. A gradient where there should be a wall. Every textbook diagram of Jupiter's interior is wrong. Every one. And here's the uncomfortable cascade. If Jupiter's core isn't what we thought, then the process that created it isn't what we thought. And if the process isn't what we thought, then every prediction we've made based on that process about Saturn, about Neptune, about the thousands of gas giants in other star systems is built on a broken foundation. This affects us more than you think. Earth exists in the shadow of Jupiter. Jupiter's gravity has been shaping our solar system for 4.5 billion years, deflecting comets, stabilizing orbits, possibly making Earth habitable. If we don't understand what Jupiter is, we don't fully understand why Earth is what it is. The catastrophe, that might explain everything. So if Jupiter did have a solid core once, what happened to it? The most violent answer: something hit it. In the early solar system, chaos reigned. Planets were migrating. Orbits were unstable. Gravitational interactions were hurling objects across billions of kilometers. The Nice model, a widely accepted framework for early solar system evolution, describes a period of upheaval so extreme it reshaped the positions of the gas giants themselves. In that chaos, one scenario keeps emerging from the simulations. A protoplanet, roughly 10 times Earth's mass, on a collision course with Jupiter. Not a glancing blow, a direct head-on impact at full speed. The energy release in that single moment exceeds anything human civilization has ever produced or witnessed, by a factor that makes the comparison meaningless. The theory: the impact shattered Jupiter's solid core, broke it apart and drove the heavy elements upward, mixing them through the planet's interior. Over billions of years, they gradually settled into the dilute, spread-out distribution Juno measured. But here's the problem. One impact may not be enough. Computer models suggest the degree of mixing Juno detected might require multiple giant impacts, or the impact combined with internal processes we haven't theorized yet, or something else entirely. Every attempt to explain the fuzzy core creates new questions that don't have answers. And this is where things get truly unsettling, because we're not just talking about Jupiter anymore. One planet, 5,000 worlds, one broken model. Here's the scale of what this means. Since 1992, we've confirmed over 5,500 exoplanets orbiting other stars. A significant portion of them are gas giants, hot Jupiters, cold Jupiters, super Jupiters, mini Neptunes, worlds we've been cataloging, classifying, and building theories around for decades. Every single classification was built on models that Jupiter just destroyed. We've been estimating which exoplanets could support atmospheres, which ones might have liquid water, which ones could theoretically host life. All of it downstream from how we understand the gas giant formation, which is downstream from how we understood Jupiter. We're not just wrong about Jupiter, we might be wrong about everything. Think about what that means. The Kepler Space Telescope, the James Webb Space Telescope, years of observation, petabytes of data, thousands of papers, scientific conferences, career-defining research, all built on a model that the largest planet in our own solar system just undermined. And that includes the planet you're standing on right now. Our understanding of why Earth is habitable, why it has liquid water, a stable orbit, a protective atmosphere is linked to Jupiter's behavior. Jupiter's gravity has been sculpting the inner solar system for billions of years. If we've been wrong about what Jupiter is, we may be wrong about why Earth works the way it does. we're not just missing a piece of the puzzle. We may be holding the wrong puzzle entirely. The magnetic field that shouldn't work this way. There's a layer to this story that almost never gets reported, and it might be the most unsettling part. Jupiter's magnetic field is the most powerful of any planet in the solar system. So vast that if you could see it with the naked eye from Earth, it would appear larger than the full moon, a structure of almost incomprehensible scale. But here's the problem. That field is generated in Jupiter's metallic hydrogen layer, the region where crushing pressure transforms hydrogen from a gas into a liquid metal that conducts electricity. As Jupiter rotates, that metallic hydrogen spins the magnetic field lines around the planet. Every calculation about how that works depends on knowing what's beneath it. The boundary, the density, the structure of the core below. With a fuzzy core, there are no clean boundaries, which means our magnetic field calculations may be fundamentally off, and this matters in an immediate, practical sense. Jupiter's radiation field, driven by that magnetic field, nearly destroyed Juno's instruments despite titanium shielding. It would be lethal to unprotected humans in minutes. Now consider this. Europa, Jupiter's moon, sits inside that radiation environment, Europa, with a confirmed liquid water ocean beneath its ice shell. Europa, one of the most scientifically compelling destinations in the solar system for the search for life. We want to send humans there eventually. We want to send probes beneath that ice. But we don't fully understand the radiation environment surrounding it because we don't fully understand what's generating it. One fuzzy core, cascading consequences all the way down to the question of whether life exists beyond Earth. Juno is still out. There, we still don't have answers. Here's what makes this even harder to sit with. Juno is still operational. Its mission has been extended multiple times. Right now, as you watch this, it is orbiting Jupiter, diving close, measuring, transmitting data back across hundreds of millions of kilometers of empty space. And we still don't know what's inside Jupiter. Teams around the world are running impact simulations, testing whether the physics of a catastrophic collision actually produces the fuzzy distribution Juno measured. Other teams are rebuilding formation models from scratch, asking whether any version of our existing theories can naturally produce a dilute core without catastrophic disruption. Some researchers have borrowed seismic techniques from geology, treating Jupiter's interior the way geologists read Earth's interior, inferring structure from how pressure waves move through it. None of them have converged on a definitive answer. Our most advanced planetary probe, years of unprecedented data, the brightest minds in planetary science, and the largest planet in our solar system is still keeping its secrets, and that's a problem we don't know how to fix. Every close pass Juno makes refines the data. Every refined dataset generates new simulations. Every new simulation raises new questions the last one couldn't answer. The more precisely we look, the deeper the mystery gets, what we're really admitting. Pull back, pull all the way back. This story isn't really about a fuzzy core. It's about the gap between what we know and what we've been acting like we know. Those are not the same thing. And for 400 years, in the case of Jupiter, we confused them. We built planetary science's most foundational models on a planet we didn't actually understand. We classified 5,500 alien worlds using frameworks built on that misunderstanding. We made predictions about which planets could harbor life based on those frameworks. We told ourselves we were filling in the details, when actually we were constructing an elaborate structure on a foundation that wasn't there. And here's what's truly unsettling. Jupiter is the easiest gas giant we have access to. It's the closest, the largest, the most studied. We've sent more missions to the Jovian system than to any other outer planet. If we got Jupiter this wrong, with all of that, what are we getting wrong about the planets we barely glanced at? What are we getting wrong about the exoplanets we've cataloged from light years away, using instruments that can only see their shadows? What are we getting wrong about Mars? About Venus? About the moons we've never properly mapped? What are we getting wrong about Earth? Science is not a collection of facts. It's a process of replacing wrong answers with less wrong answers. Forced a replacement. A significant, uncomfortable field reshaping replacement. That's the process working. But it's also a reminder, every confident claim in science carries a hidden asterisk. Every model is only as good as the data that built it. Every discovery we celebrate is standing on assumptions we haven't tested yet. Jupiter was the assumption we all agreed on. Jupiter was the template. Jupiter was the thing we thought we knew. And Jupiter was wrong. And if Jupiter can be this wrong, what else are we completely blind to right now?